Okay, now we're going to learn something that is the easiest part about magnetic circuits. And all it is relative permeability. So this is our formula for relative permeability. Let's remember this part. This is pretty easy, okay? This is relative permeability. Now, permeability has the nice symbol like this. It's called a mu. Relative permeability has the symbol mu with an R beside it because it's relative. The relative permeability is a ratio of a permeability of something over a permeability of something else with a naught beside it. And this something else is free space. This is relative permeability. Relative permeability is the permeability. It's just the permeability of what you're looking at over permeability of something really special that we use as a reference. And that's called free space. It's just something really special. So, first of all, I have to review what permeability is. So we have to know that permeability, whoops, that permeability is how permissible or how permeable this material is, how permissible it is for these lines of flux to be established inside this magnetic circuit. We have lines of flux. They got established by a bunch of coils with current running through them. There's current running through them times the number of coils, and that sort of induced this magnetism, which is magnetic flux. And if it's really permeable material, we call that PM, is permeable. But we like to compare materials. If we look at the material property of something that is permeable, material property, if we look at it as a material property, we say permeability is equal to the permeance in general for this whole circuit times a geometry normalizing. So that is the permeance, how happy we are to establish as the magnetic flux, times the length over cross-sectional area. It's the length of the circuit that each flux line travels, give or take, is actually average, divided by the cross-sectional area in which it has to travel and all these flux lines are going through. So it's the normalized geometry of permeance is the material property permeability. So now we can compare materials with really big circuits and really small circuits because we have this term permeability. We took it now one step forward and we said, there's a special permeability. It's that of a vacuum or free space. And let's call that mu naught. It's like a starting point. And mu naught has a value. If I were to calculate or do an experiment about how permeable a vacuum is, I would learn that mu naught, or the permeability in a vacuum or free space, is actually 4 times pi times 10 to the negative 7 units of permeability, which is Weber per amp times the number of turns that established that that magnetic field times the length in meters divided by the area in meters squared. which is 4 pi times 10 to the negative 7 Weber per amp turn, if you want to keep that as like a fake unit, meters when we cross these out. And we measured that. Somebody measured this and said in free space, that's what it is. It is not a lot, not very permeable. So free space doesn't want a magnetic field to be induced in it. This shouldn't be surprising to us. This is why we can have things like the induction stoves, where you put a ferromagnetic material with your water in it on the stove, and
is a lot like writing a song, you know.
so we can put this ferromagnetic material sitting on the stove, and that this magnetic field is going to stay inside that ferromagnetic material. It's not going to creep out into free space and get you, because you're not a ferromagnetic material, because that free space in between you and that pot is not very permeable. So we like to compare things. We like to compare our materials to things that are not very permeable. We like to be precise, and we like to compare our materials, the permeability of our material, to exactly a permeability that we know to be pretty much nothing. And that is mu naught, which is the permeability of free space. Now, I'd like to also say that we can assume that the permeability of brass equals the permeability of plastic equals the permeability of air equals the permeability of cardboard, which seems kind of random, but it's not, because we have some devices that are made of cardboard or fiberboard. And we're going to assume that all of these are equal to that of free space. Is it true? No. Permeability of brass and plastic and air and cardboard are a little bit higher than that of free space or that of a vacuum. But for our purposes in the science that we are going to be doing or calculating, is so small that we can assume that the permeability of free space is the same number. It's 4 pi times 10 to the negative 7 as all of these other things that are basically non-ferromagnetic. All right, so we just have this ratio, very, very easy ratio. It's the relative permeability, is the permeability of what I care about over here. This has a permeability over that of free space.